So now let's look at solids in solution. It says when a solid substance dissolves in a liquid, the solute particles are attracted to the solvent particles. All right, so there's going to be an attraction between the liquid and then the solid that you're trying to dissolve. When the solution forms, the solute particles are more strongly attracted to the solvent than to each other. So the solid that you've put into your liquid already have an attraction between each other. And what this is saying is that the liquid you place them in will have a greater attraction for those solid particles than they do for themselves. Now, just like liquids, an important idea is applying the like dissolves like rule. So that also, now for gases, that doesn't matter. Gases are so far apart, they don't have intermolecular forces, and so they mix freely with each other, freely and uniformly. But solids and liquids both have intermolecular forces, and so there's different things at work here, and so we have to apply the like dissolves like rule. So on this table, this is a summary for solids, and really the only thing that's added here are the ionic compounds. So again, you'll see that we have polar is soluble in polar and insoluble in nonpolar. Let me back up because I didn't even mention the words. So we're not using the words miscible and immiscible anymore, are we? Here, when we talk about a solid that dissolves, this is called soluble. Okay, so we're not using miscible and immiscible. And then a solid does not dissolve. In a liquid. This is called insoluble. Okay, so these are the words that are down in the table. So you see the like dissolves like, which again means the closer two substances are in polarity, the more likely they will dissolve with each other or mix with each other. So a polar solid would dissolve in a polar solvent, but not in a nonpolar solvent. Okay, that's the same as a liquid. A nonpolar solid will dissolve in a nonpolar solvent, but not in a polar solvent. But then finally, here's the new one. We have ionic compounds. So some solids are ionic, and we can determine if they're ionic because they'll have a metal plus a nonmetal. Now, ionic have charges, right? They contain ions. And ions have a plus and a minus charge. So ionic compounds are most like polar solvents because polar solvents have a dipole, and the dipole has the partial plus and partial minus. So ionic solids are more likely to be soluble in a polar solvent. They are closer to each other than in a non-polar solvent. So ionic substances will dissolve in polar in general and not nonpolar. We also know, though, even just for water, we had a solubility chart in one of our previous chapters, and we know not all ionic substances are soluble in water. So it's not a blanket statement, but if I had to choose without a solubility chart, ionic would be more likely to dissolve in a polar substance. So I have two images. Oh, no, this is like dissolves like, and then I have two images, sorry. So here's some examples. It says ionic compounds like sodium chloride, so salt, are soluble in polar solvents like water and insoluble in nonpolar solvents. Polar compounds like table sugar are soluble in polar solvents like water and insoluble in nonpolar solvents. And nonpolar compounds like naphthalene, which is the chemical in mothballs, are soluble in nonpolar solvents and insoluble in polar solvents. So we're looking for like dissolves like. So ionic is more like polar. Okay? Polar likes polar. Nonpolar likes nonpolar. Now, let's take a look, because it talked about in the previous slide that the liquid has a greater attraction for the solid than the solid has within itself. Let's try to look at an illustration that shows us this. So this says molecular compounds, and I've mentioned this before, but molecular compounds are referring to covalent compounds because things with covalent bonds form molecules. And so how we know that something's covalent is it would be nonmetals. So when you put something like sugar would fall in this category, into water, it will slowly begin to dissolve. Oh, and they're using sugar here. Now all of a sudden, I see it says when a sugar crystal is placed in water, the water molecules attack the crystal and they pull it away from the solute. So they come around the crystal and they start pulling the sugar crystal and they start pulling it into the water. The sugar molecules are held within a cluster of waters, which is a solvent cage. And that's what they're trying to show you here. The red around it is the water. This is the water. And in the middle is a sugar molecule. So the sugar isn't next to any sugar. Once it dissolves, you have sugar and it's surrounded by water. Sugar will stir. Oh, I was going to say something that's in a future slide. So never mind. I'm not going to say it. We'll wait and see. Now, ionic compounds are very similar, except ionic compounds have both positives and negatives. So again, the water molecules are going to come and attack the crystals. But water, remember, has a dipole. The oxygen is negative and the hydrogens are positive. So now we have, if I had sodium chloride, which has sodium ions and chloride ions. So if a water molecule was here, if I had a sodium ion, which is a positive, then the oxygens would surround the sodium ion. These are my little waters. They look funny. Because the oxygen all has negative, right? So they're all going to be attracted to the sodium ion and they'll form that little water cage around it. And then the chloride ions, they're negative. And so what we find is that the oxygen doesn't go toward them, but the hydrogen do. Whoops. And I kind of wrote myself into a corner. And that's because the hydrogen all have positive. So they want to all be around the chloride ion. Now, as a consequence, remember in a past chapter, I've mentioned that ionic compounds dissociate when dissolved. Oh no. Okay, I'm going to erase a little bit of my hydrogens, okay?